This next example of superposition is one that we enjoy every day. It leads to musical tones and instruments, stringed, tubed instruments. It's applicable in so many different things. So, as an example, to start, let's suppose I have a string, and what this complicated looking graph is, these are going to be different time intervals, sequential time intervals. Okay, so this would be one time, another time, and so on and so forth. And I've drawn this string attached to 2 points. Okay, that's what these walls are supposed to be. These dotted lines are to help me keep the segments of the string organized so I can see how a piece of string here compares to it later on. So these dotted lines are just kind of a grid to help us keep the motion compared correctly from time to time. So let's suppose that on this side right here, I'm wiggling this string up and down at some set frequency. I've got it hooked to an oscillator, and it's wiggling up and down at some frequency. Well, initially, I first give it its first starting to wiggle. That pulse will start to travel along, but since I continue to wiggle it in a sinusoidal way, it will create a sinusoidal wave that will travel away from this point. Okay, and let's suppose at this moment in time, just this one moment in time, the wave looks perfectly sinusoidal. Okay, so between the ends of the string, this frequency is such that I can create 3 bumps, or 1.5 wavelengths of this string. So this frequency is causing, or the disturbance on this side, the left side of the string, is causing that wave. Okay, now imagine that a friend has an oscillator on this side and is causing it to oscillate up and down as well at the exact same frequency and same amplitude. Okay, and started it at just the right time so that at this moment in time his wave had traveled or crossed, and at this moment of time it looks perfectly sinusoidal for this oscillator. So I'm going to draw a dotted line, so they'd be one on top of the other. I'm just going to draw a dotted line to emphasize that the other wave has gone the other direction, and at this moment in time they are doing the same thing to the string. Okay? Now you have to remember that this wave is traveling that way, and this wave, I'll do dots like that, is traveling this way. Okay, so the one from the left is traveling away from its source, and this one is traveling away from its source. So at this moment in time they look like that, and we know by superposition that we can add the effect together to get the overall shape of the string at this moment in time. So they're both 0 here, so it's going to stay 0. They're both at maximum amplitude here, so it's going to be double. They're both 0 here, so that should stay 0. They're both at negative maximum amplitude, so that's going to be double, and so on and so forth. Okay, so I can connect those dots, and I end up with a same sinusoidal curve, but it's twice the amplitude. Same wavelength, but twice the amplitude. Okay, now let's imagine that we've waited just enough time, a fraction of a cycle or a fraction of a period, such that the rightward going wave, the solid line I've drawn, has moved a quarter of a wavelength. So now the tail is right here, okay, and so it actually looks like that. Okay, so this is a quarter of a cycle later, and it's moved to there. Still moving on this direction. Okay, well, where is this dotted pulse or dotted wave going? It's moving that way, so instead of coming out of the origin here, it's coming out right here. So I'm going to end up with something that looks like this. Okay, and it's still moving that direction. Okay, so I can like that and like that. Okay, well at this moment in time, 1/4 cycle later than this time, I can do superposition, add these together, but look what I get. I get positive amplitude and negative amplitude, 0. quarter or some fraction of positive, same fraction of negative, 0, 0, 0, 0 all the way across. At this moment in time, according to superposition, that string is not displaced. It's at its equilibrium point. Okay, now we showed in a previous video how remarkable that is, and we can see it with high-speed imaging. You can see a string actually look flat, and a moment later it's displaced everywhere. Okay, so it is a true principle that we can experimentally verify. Okay, so we're going to try and go through the quantitative reasoning for it. Okay, so according to superposition, this is totally flat. A quarter cycle earlier, it had double the amplitude. Okay, same wavelength, but double the amplitude. Here it's totally flat. Let's go 1 quarter cycle later. Okay, so now this point is moved to here, which means this point's moved to here, and therefore we're going to come out like this, and the cycle's going to look like that. So it's going to kind of be the upside down of the first picture we had. Okay, so hopefully you can see if I shift this 1 quarter cycle further, this point gets to the end, I have the upside down bump, right side bump in the center, and a full upside down bump here. Likewise, if the dotted one goes further that way, this now gets to the end, and I have it looking like this. And those truly are at the same point if they're identical waves, only opposite directions. I'm just offsetting it so we can see it. So now by superposition, well, we have double negative here, double positive here, double negative here, 0, 0, 0, and 0. And so I get something that looks like that. Okay. So I've now created 3 snapshots. Let's go do this next 2 fairly quickly. The next cycle, if I move it a little bit further, the 0 is going to come to here, and so it's going to actually look like that. Okay, the 0 here is going to move over to that far, so it's going to look like that, and we can do the same thing here. See that that's going to be a flat line. Again, I think it's totally amazing that the momentum carries through. At this one point in time, it looks like a stationary string, but in fact, those pieces of string are moving. It's just they're all in sequence at the equilibrium point, but ready with momentum to move away from equilibrium. So that's what the string would look like at this point in time, and then 1 quarter cycle later. Okay, so this dotted line gets 1 quarter cycle further, so it looks like this. Okay, this one gets a quarter cycle further, and it's going to look the same. Again, offsetting it only so we can visually see it, and those are now maximum double or positive double, negative double, positive double, 0, 0, 0, 0, and I get my double, and I'm back to what it looks like here. Now I could keep doing that, and I didn't show intermediate steps, 1/8 of a cycle or 1/16 of a cycle, but what is really amazing, and that we can pull just from these pictures, and is true for all times, is that when you are looking at this string with these 2 frequencies oscillating with the same frequency, or these 2 oscillators with the same frequency, causing the same wavelengths, and set just right so they are overlapping at these times, that it looks like the bumps are just going from up to down to up, we'd see down, and so on and so forth, with these segments where it's just flat in between. And our traveling waves don't seem to be traveling anymore. If I were to map that, it'd be double high, double low, double high, double low, double high, double low, and it would look like it's not moving, traveling anymore, but just oscillating in place. These bumps seem to oscillate in place, up and down, such that at points in time, the whole string lays flat at certain points in time. Okay, This effect is called a standing wave and happens in nearly every musical instrument, where we create certain tones and are able to control parameters like the length of the string and the frequency. And we're going to find later that only certain frequencies are allowed to create a standing wave based on the boundary conditions of the medium, the string or the air molecules inside a tube. But the standing wave basically takes these two traveling waves that are traveling in opposite directions and turns them into a standing wave where the bumps just change positive to negative, but they don't travel anymore.